Okay, this is attempt 3 at explaining some problems there are with the standard model of cosmology as far as the sun's path around the Earth. And one of these problems, I hope I can improve what I'm trying to convey with this illustration here. And as you can see, I picked the June solstice just to pick a spot. And this drawing is what I'm hoping to explain what the problem is by explaining, first of all, the standard model and why I don't think it works. So let me explain each of the parts here. And what we got here, first of all, is, whoops, didn't want to roll that far. Polaris is what determines true north. Okay, it's not magnetic north. It's north is determined by the point of the Earth that aims at Polaris. That's how we determine true north. And true north and magnetic north always have to be both considered when people are navigating in a boat or an airplane or something like that. So that's where north and south come from. They don't come from the Earth's magnetic poles, although they're close, but those magnetic poles move a little bit, and they're not directly aligned with true north. So, like, for example, when you do a sundial, you have to find true north or it won't work. And on this ball here, we got, first of all, up is any way away from the center. Here's the center. This line comes out here. I don't know if you can see it. I could try to magnify that a little bit more so you can see that line. And it starts from the center, goes out any direction, toward you, away from you, at any angle. That's up. Okay? That's how up is defined on a ball. So it could be up here, it could be up here, anywhere. Now these three inner discs that are perpendicular to the north-south line, okay? I got a blue disc here, a red disc in the middle, a green disc on top. This is any northern latitude. This is any southern latitude. These are not necessarily the tropics. This is the equator. Okay, I'm just drawing a line around the ball. That's all I'm doing. At different points on the ball along this north-south axis. This is the axis on which the Earth turns. So if you were to, say, put a ball, a rubber ball, and put a stick right through the middle, okay, ball on a stick, that's what we've got here. The stick points to Polaris, okay? That's true north. The stick points to Polaris. And if the ball had say, like a marble, that sometimes you get marbles, you know, play marbles that have little things on the inside. These things are perpendicular, that is to say a right angle to the stick through the ball, okay? And if you trace that line around the outside of the ball, this one would be the equator. This one would be some southern latitude. This one would be some northern latitude. Now, I happen to live in a northern latitude, so this is an area roughly where I would be, okay? So, and as I said, up is anywhere from the center, a straight line out toward the surface of the ball in any direction, okay? Now, let me back this out. Well, maybe I won't back it out yet. This yellow line and this yellow line and this yellow line represent the path of the sun at that day, okay? The June solstice. This is observed. This is not theory. When we had the solstice, I got a couple of different compasses, analog compasses, and saw that the sun was rising a little bit north of east, okay? The reason this end of this yellow line here is above the green is because it's north. North being toward Polaris, okay? Not up. Not toward the surface, but toward Polaris. That's north. So this line on the west side is also up not, I'm sorry, I used the wrong term. I had up on my brain. North, not up, but north. That is to say, this direction inside the, or along the surface of the ball going toward Polaris, that's north. Both ends of this line are north of my latitude. Okay, this is me at my latitude, this little dot, these are the observers. So I'm here. I saw the sun rise north of east, set north of west, and at its zenith, that is to say its highest point, solar noon, it was south of my latitude. You see what I'm saying? This way is north, this way is south. The sun started north of my latitude, it went south of it, and then it went north again. This is verified by timeanddate.com, and I've been watching it all summer, comparing it to timeanddate.com, and check the angle. When you have to know what you're reading when you read those sites, and the angle, it'll say so many degrees east, northeast for sunrise on that day. And what that means is if you point your compass or, look at true north close enough for, just checking where the sun's rising, it will say so many degrees, and that's from north. North is 0 or 360, okay, because the circle has 360 degrees. So it'll say, for example, due east would be 90 degrees from north. So if it's a little bit north of east, it will be something like 80 degrees or 85 degrees east, northeast. Okay, so anyway, all that is to say that the sun rose and set north of my latitude and had its zenith south of my latitude, remembering that north is toward Polaris, south is away from Polaris. And so north and south along the edge of this ball, north is going to be that way, south is going to be that way, and that's what the sun did. It went at an angle down across my latitude. Here's my latitude, going around the outside of the ball, parallel with the equator, perpendicular to the pole, the axis. Here's the path of the sun, okay? And here's that same path at the equator. It's parallel with the equator, but north of it. At the opposite solstice, the December solstice, this line would be below that red disk, okay? At the equinox, it'll be right on it. But we're doing June solstice, so it's north of it. Same way, and I see a little piece I need to erase there on, let's see, the ball part here. I have to fix it because I'm obsessive compulsive or something. I have to find my south latitude sun path. There it is. Get my eraser and get rid of, well, my eraser's just too small. We'll fix that problem. Get rid of that. It's bothering me. There, gone. Okay, now. There we go, back to the angles. Now you see something curious. The north and south sun angles pinch toward the middle. That is to say, the zenith of the sun, compared to where it rises and sets, leans toward the equator. Okay? You see what I'm saying? Here's 3 observers. If you're at the equator, the sun will always rise and set due east, due west, but that arc will be either more toward the north or more toward the south, but it will always be parallel to the equator. That's how things are at the equator. But at any latitude beyond that, around this ball, the sun will, at the June solstice, be more north. It is for all 3 of these, more north from the southern latitude, and more north from here. But look at this. This one is more south. Still, I mean, it's not as south as it would be at any other time of the year. Throughout the year, if you take this yellow thing and rotate it, it's going to face more south as the sun, this one goes down. That's the thing about the seasons, that this line from one solstice to the other will start here. It'll go down to here at the equinox, back and down to here at the winter solstice, the December one. Then it will come back up, and it keeps oscillating between here and here, but it always stays parallel. While that's going on, these, like this one, is at its highest point. It's most parallel point it's going to get. It's always still going to be angled down. As the sun moves south during the season, this end will point, the whole thing will drift down. All these lines will drift up and down. You see what I'm saying? But they're always going to have this kind of an angle. It'll vary a little bit. But the point is that where it rises and sets, the zenith in the northern hemisphere will be south of that. In the southern hemisphere, it will be north of that. It has to be, because if the sun is here, then the highest point of the sun as it goes around the earth, because we're doing this from earth perspective, is always going to be toward the sun. Okay? Now you know why this path is the theoretical path that does not work. Because, let me back out a little bit here. There's the sun. That's its 23.405 angle from the Earth pointing north. This is the Earth's axis pointing toward Polaris. The sun is at this angle while the Earth is spinning. See this inner arrow? Let me go back in here so you can see it. This gray arrow on the inside, that's the direction of Earth spin. Okay? That's what, if the Earth is spinning, that's what causes the sun to appear to go the opposite way. So if you had a stationary light here, you spin the ball, around this way, the sun will appear to be going this way, okay? But the sun is at an angle to this line. It's not, if you extend straight out from the equator, that's not where the sun is. It's up 23.405 degrees. Okay? That's where the sun is. If it were here, this would make sense. But it's not. It's up here. The Earth is tilted toward the sun in the summer in the northern latitudes. At June, this part of the world is tilted this way, so that the sun is this angle from us. In the December, picture moving the sun over here. Okay? That's allegedly just the Earth's spinning on this axis while going around the sun and, tilted at this angle, so that in the winter, and let me go get an image of that real quick, because I know that's hard to visualize. And somewhere I have, whoops, I opened the wrong folder there. Sorry about that. Let me, it's going to take too long. I don't know. Bear with me for a second here. Let me try to find that, because I need to show you what's going on there. All right, let me stop screen sharing that, go get something different. That's this one. And share, present. Okay. Hopefully you can see this. This is what I'm saying. The standard model is that June solstice over here, the Earth is tilted like this. Here's that stick through the ball. There's the way the Earth is spinning. There's June solstice. The sun is at, if you go back to my drawing, the sun is up to the right, according to if we turn this Earth so it's this pole is straight up and down. I got too many images to show at once. I need animation or something. But anyway, this is the theory that the reason the Earth's northern hemisphere is tilted toward the sun in the June and away from the sun in December is why the sun moves along this path, this arc. And let me see if I can find here, this one is allegedly the whole picture. Here's an equinox. The Earth is still tilted. Polaris is up here someplace. Okay. The Earth is always tilted toward Polaris, always this angle, but spinning around that pole, that axis, as it goes. And different times of the year, like, for example, June solstice, here's the north half of the Earth pointing toward the sun at an angle, see, because it isn't running parallel to its orbit line. It's angled in toward it here. Well, at the opposite end in December, the bottom end is angled toward the sun. And at the equinoxes, the sun is facing straight on to, the whole north and south, but the Earth is still angled. Try and keep that in mind because it's going to get interesting. Okay, now let me go back to my drawing and present that. So you can see what I'm saying. All I did was straighten up the Earth so the ball on the stick is pointing straight up. That means the sun has to angle up to match it because we're doing this from Earth perspective now, and we're at latitudes, which is parallel lines around the outside of the ball, but they're at an angle to the sun. Observed path of the sun is to go north, June solstice, north and east and west setting, rising and setting is north of the latitude. Every latitude, the sun is rising and setting north, but as it goes around the Earth, it dips toward the equator. Okay? This one doesn't have to dip. It's already toward the equator. This one has to dip north. This one dips south. How is that possible if the sun is going like this? That's what doesn't make sense. Okay? If the sun is at such an angle that it's going around the Earth like this, which it would be if you went back to that other thing I just showed you, the Earth is tilted and spinning on that tilt and going around the sun. This is, from our perspective, what the sun is doing. Okay? Does that, it kind of matches the southern latitude path, but not the equator and not the north. Does not work. It can't work. Like I said, these yellow little arcs here are observations. You can't argue with those. And you can go on timeanddate.com and verify, but you can measure these locally. And it stretches credulity to think that all these observers and amateur astronomers have never noticed that the sun doesn't follow the path of timeanddate.com. It does. At least here I can verify it. Okay? And I'm pretty sure anybody who's lived at the equator would verify this. And we've all heard about the fact that normal sundials don't work there because it doesn't tilt. So you won't get a shadow except going directly east or west. The shadow would only be longest at sunrise and sunset and no shadow at all at noon. So we know that this is accurate. These yellow lines represent what the sun's actually going to do. And when you think about it, since the sun is toward the equator within those, remember that arc, the high point of the day is always going to, when the sun is most visible for whatever longitude which we are on, which is the outside arc. If you follow like from where I live to someone in, of course, directly below me in the United States, there's nothing but ocean, but pick any latitude, say the UK. Below them would be like the Middle East, Northern Africa, and then you go down here eventually, depending on the latitude, you hit Australia. That's the longitude line, and so if the sun is within the tropics, everything outside of the tropics is always going to see a tilt toward the equator. Within the tropics, that's the limits to which this line can remain parallel, which is to say it rises in the east goes directly overhead, no shadow, 90 degrees. That's 90 degrees from your surface. You're looking 90 degrees to the sun, and then directly west. That can only happen within the tropics. It will happen in the tropic. The northern one is the Tropic of Cancer. Say, pretend that this line right now is the Tropic of Cancer at the summer solstice. And if that's why they call it a solstice. It's from a Greek word meaning to turn. It's the point at which the sun turns back in its seasonal path. Okay, so that's why they call them tropics. It's from the Greek word tropos. And so this is the northern tropic because it's the June solstice. So this is the Tropic of Cancer. The opposite side of that red disk, when the yellow line drops down here, that would be the Tropic of Capricorn in the southern hemisphere, and that would be the December solstice. So it's a very somewhat narrow range at this, because even the U.S., the entire U.S. is above the Tropic of Cancer. That tropic line goes through Mexico, actually. So, and this line happens to be way above the tropics. So it's probably, don't worry about what's actually there. I'm just doing this for illustration that we're above the tropic zone. And likewise, this southern latitude is below the tropic zone. So the sun tilt has to go toward the equator in both cases. But none of that makes sense except the southern one in the summer with this path of the sun as per the theory as to explaining the seasons. If you have a spinning ball spinning on this axis that points toward Polaris rather than the sun, and that the sun is, the Earth is going around it with that tilt, this is what you get. The sun going north and then south. See, this is north and south. The sun is going north along its path and then south. There's no denying this on the standard models. Doesn't work. You can't explain, and the June solstice, you cannot explain anything but the southern path that sort of kind of matches that. You can't do it. And of course, you have the opposite mirror image problem in the December solstice. At the equinox, all of these are going to pinch toward the middle, and yet this one, neither of these will make sense as the sun's path, because if the sun is still going to be at an angle, it's not going to work. Now, I want to show you something about what could possibly work. This is called a diverging lens. Light comes from here. Here's the sun, hits this concave surface, and the light spreads out like this. I can verify this with lenses. I've done it at physics class at college. This is not made up mathematical nonsense. This is experiment. This is just a depiction of the experiment. You can find actual pictures. I have some. Maybe I'll show you those later, but I will show you the one on the opposite, the converging lens, which means on the other, they're concave and they squish down on the other side. But the light's coming this way, and the only way to make a sun that's going at, say this is the equator, northern latitudes, southern latitudes, this would explain those angles. See, if we're here, this is northern latitudes, say these are the two solstices. These are the limits of, say these are the tropics. This is, we're always going to see the sun at an extreme angle at the June solstice, a less extreme angle at the December one, but they're both still aiming down toward the equator. Opposite problem in the south, not problem necessarily, but that's what we've observed. The south is always going to angle up. The north is always going to angle down. Equator will always be straight. The only way you can get that with one sun is if the sun within this, narrow range where you'd still get a straight line, has this kind of a lens around it or between it and the Earth somewhere that causes this kind of motion. Okay, and even then, this is just a snapshot of time. You would have to have, I think, the Earth surrounded by this kind of lens shape in order to make a sun moving around the equator look like this through its path on a given day. Okay? I mean, this is the sun's path on a day. One day it's going to make this circle. So this has to work from every angle. So whether you have the sun moving around the Earth, like as in geocentrism, which is this basically what this is depicting, even though the angles match the globe model, the only difference between a globe geocentric model and the standard heliocentric model is which thing is moving and spinning. So it doesn't make any difference from our perspective. What we see standing on the surface of these ball, where these dots are on the surface, is that the sun does this. I'm sorry, the sun does these yellow lines. The theory doesn't work with that. The only way, this observation with these three lines, these yellow lines, the only way that works is with this kind of a lens between us and the sun. And I'm not sure if it matters whether this is around the Earth or around the sun, as long as it has this shape, because it's curving toward each. Say if the Earth is over here, if the Earth is curved, it's looking into a concave lens. So is the sun. It's the only way I can think of to make this work. Now let me go down here to this one. Let me back out just a bit. Let me go to like, let's see if I can get 75%. Can't do that. I have to key it in. Whoops, that's 750. I don't want that. 75. All right. I had to take a picture that I found in Google Images and slant it so it would match our parallel sun. I didn't rotate it quite enough. You can see there's a little slanted. But the point is, this globe is time zones imposed upon it. So this is a standard model of time zones, and we know this works because, say, for example, in the eastern United States, Eastern Standard Time, that you can draw a line down the East Coast through a little bit edge of the Midwest here, and up to Canada, down to Central America. That's all experiencing daytime at the same time. Different degrees of daytime. The farther away you get from where you are currently, the darker it's going to be. That's the terminator line. If you shine a flashlight at a ball and hold the ball in front of you, hold the flashlight in one hand, pointing straight at the ball, the terminator line, the shadow line, will be exactly in line with that light, always. And I've showed that in my moon video. If you shine a flashlight at a ball, the line is going to be straight, okay? It's going to go straight as far as, it'll follow the curve of the ball, but if you look at it straight on, like from this angle, you're going to see a straight line. I showed that in my moon experiment video, okay? Any kind of a light shining at any ball would give you that. So as you move the light around the ball, you're going to see the shadow line move like this. So time zones on a ball makes sense for that model. This is observation. We know that if you travel to the next time zone, it's, suddenly, instantly, it's going to still be dark there. Okay. Or, an hour later. We know in the US, for example, we got Eastern, Central, Mountain, Pacific. So we got 4 different hours, 4 time zones. So the sun is going this way around us that we get. Now, what did I say? Remember about how this line that's why I drew this line from here's where the sun must be to make these time zones make sense. But that's not where the sun is it? Let me back down. Let's go to 50%. See the problem? This is north. This is pointing to Polaris. Okay, I turned this picture this way so this would line up with our north up here. All right. What's the problem? In order to make time zones work on the ball model, the sun must be exactly traveling across the world at the equator line. But it's not, it's up here. It's up at an angle. So the time zone should be angled like this to match it. See the sun up here? The time zone, the terminator line should be this line. That's why I happen to draw that up line over there, and that this way is around the ball, this way is north, this way is south. Look at this up line from the center. That's the shadow line, the terminator line, that you should get from a sun at a 23.45 degree angle. But you don't. You get this. The sun is not in the right place. According to their own model, they can't make time zones work with the sun at 23.45 degrees. They can't do it. Time zones should be going at an angle like this to match the path of the sun through their, according to their theory. That's where the terminator line should be. Doesn't make sense to me. Okay? So we're working with the ball model to make everybody happy. Nobody can dispute that this is the angle of the sun. I know I didn't precisely do that. This is not AutoCAD, but you get the idea. Then I showed you with the other picture why this works, that this is about 23 or so degrees off from vertical, from the horizontal line. If you stretched a line from the equator straight out, like I did here, knowing that north is north, these are matched up. Both of these are pointing at Polaris. That's why it's called north. And in order for time zones to work, and we know this is observational time zones, if you live in this spot, regardless of the shape of this thing, the fact is that you can draw a line, you know, maybe on a different shape Earth that these continents aren't where we think they are and so forth. But working with just the ball model right now, later, you know, maybe another time I can do different flat Earth shapes to see what the problems are with those, because I think they all have critical problems with sun movement. At any rate, right now it's the ball. And right now it's from our Earth's perspective, as if the Earth is still, and nobody in the ball Earth model has a problem with understanding it this way. I've looked it up. And so knowing that I'm matching up north here, that the sun is supposed to be up here, the terminator line, which is to say the time zone line, should be at an angle, and they're not. And I don't know how anybody's going to solve that problem. As for the other, looking at the chat, that's a good question about the other time of year. If the sun's over here, the angle is the same. The angle is always going to be the same. It's just that basically, instead of this half of the Earth looking at, it's this half, but it's the same angle. I don't think the angle would make any difference. But then we'd have a season issue. That's the problem, is supposedly then it's cold down here, but why if the Earth is at the same angle? And if you go back to that other drawing where you saw the 4 Earths at different seasons, the solstices and equinoxes around the central sun, that's how they try to explain seasons, but the angle is always the same. So I would think the time zone angle would remain consistent, but I'd have to think about that some more. But that's a good question. Anyway, the problem is, like I said, how can you have time zone lines that are in alignment with the north-south line? In other words, the time zone lines point toward Polaris, just like, they point true north on any map. Then the sun cannot be at this angle up here. Right? So in the chat, if you think that the angle would change, explain it, please, because I don't see how. Because if the sun is this angle in the June, it's going to be over here. You still have the same tilt. The tilt is always the same. Which end is pointing toward the sun changes, but the sun is going to move across like this, okay? At the equinox, it's going to be right here. All right. So I think I see what you're saying now, because suppose the sun is right here, as it would be at the equinox. Where's the terminator line? It's going to be around here. Straight up, it's going to be straight up and down. You're right. And then when it goes over here, the terminator line is still at this angle. The only time it changes is at the equinox. So let me think about that some more. Because right now, like I said, right now, this doesn't work, but pretend you take this line in this sun and move it up over here. It's pointing like this. So we have a terminator line going this way, just like I have up here. Terminator line going this way. As the sun moves this way across the Earth, because it's got to move like this, I think the top one would be a little easier to see. Moving like this, yeah, even though the Earth is still tilted away from it, the rotation this way from the sun still wouldn't change. The terminator line would be straight up and down from north to south. But then when it goes over here, it's going to go back to the same angle. So it's going to change from straight to this angle, the 23.5 angle. Because even if the angle is this way, that the sun is down here, you're still going to have the light source and the parallel line to it. So it will vary, but it will only vary 23.5 degrees. But it will vary. That's the key. I'm glad you asked the question, because time zones don't vary by observation. But according to the standard movement of the sun around the Earth, the time zone at the equinox, when the sun is here, that wouldn't work. Now let me go back to see if I can find, where was that picture? The Earth Seasons one. Let me share that. All right. Yeah, so even in this model, sorry about the silence there, I was thinking. Here's north. The time zones are going according to this line. Remember, this time zones face Polaris. They follow the ball on the stick in the ball and going through the center, pointing toward Polaris. That's the terminator line, or I'm sorry, that's the time zone line. But when it's tilted, it should be this line, and it's not. That's where the terminator line will be if the sun is here in relation to the Earth. This is their standard cosmology. The time zone should be at that angle, 23.5 degrees off, and they're not. And that's the problem. It doesn't matter which way it tilts. The fact that it moves, the fact that the angle of the terminator line moves, is disproving the standard model, because the time zones don't tilt. They don't move. They're exactly in line with that stick through the ball. They're in line with this. They're in line, or I'm sorry, the time zones are aligned with the because theirs is tilted. I forgot I wasn't using my drawing. They're in line with this. That's where the time zone lines are. But the terminator line's going this way. So, and it's varying at least between these 2 points. The fact that this line is changing, but the time zone lines are not, that's where the problem is. I'm talking about terminator lines too. That the time zone is when we go by where the entire length of the sun's path from sunrise to sunset. Yes, I know that if you want to compare one time zone to another, I'm just saying what a zone is, because there's daylight from the time the sun rises to the time the sun sets. And that's a time zone. Okay, but I mean, that's the length of the, let me go back to my other drawing and just so I can show you what I'm talking about here. This one. Okay, these slices are like, there's the space of daylight from sunrise to sunset. Okay, now if you compare the sunrise of one to the sunrise of the next, that's an hour difference. That's a 15-degree difference. Okay, but the terminator line is the leading edge of the shadow, or the following edge of the shadow. So that's the lines between are the terminator lines of the sun. That's why we have time zones. They're following the terminator line. Otherwise, you would have a situation where if it doesn't follow the terminator line, you would have a situation where daytime is cutting through like this. That's the problem. You would have daytime cutting through like this, or at this angle if you prefer. Let's use this handy box here that got rotated when everything else did. The daylight line would be going like that if the sun was at its proper position up here. This is your terminator line. How can you have a terminator line that is not lined up with time zone line? You can't. There's no way you can do that. Terminator line is where the line is between light and dark. That's the definition of a terminator line. A time zone, while it is defined by some position, it takes 15 degrees for the sun to go from sunrise to sunset. And this takes, the number of hours depends upon the season. But the fact is that the reason we have time zones is because we're following daylight, the edge of daylight as it moves around the earth. Okay? We're following the edge of daylight as it moves around the earth. That's what time zones are. They're marking the terminator lines as the sun goes around. Because if you see the sun going around here, there's going to be a terminator line facing the sun that, you could draw a line directly from there to the sun, which is how it is in this drawing. We have, if the sun was down here, these would match the terminator line. But the sun is up here. So the time zone line should be going like that. You see what I'm saying? Because nobody can dispute that this is how time zones work. They run in the hours depending on the sun going across here, okay? But why, if we have daylight here, darkness here, there's a line between daytime and nighttime, okay? Day here, night here, there's a line between them, okay? That line will move across the face of the ball throughout the day. And the time zones is still dark here. When it moves, this one becomes light. And it does so along this line. And the reason we have those time zones along these lines is because they're perpendicular to the sun. Time zones are not, they're observed. If you were to travel, you freeze time right here, and you travel from this farthest point north on the U.S., travel down to Central America, and do that instantly at that freeze in time, you will be on the line between, you will be at sunset, basically, or sunrise, depending on which way you want to look. And the only way that that's possible is if the sun is this way to the line. Okay? That's a time zone line, terminator line. We have time zones because of terminator lines. That's what the edge between a time zone and one time zone and another is. It's a terminator line. That's why we have those. And the fact that this is observed, if you go travel down through here, you observe that this line between light and dark runs parallel to the north-south line. But the sun is not going around the equator all the time. It's varying. It's up here, and the sun is always, the Earth is always tilted to the sun. But like I said, at the equinox, the terminator line will go straight up and down, but not any time after that, because the sun is going like this, not like this. That's why we supposedly have seasons. So go read up on terminator lines and time zones, the relationship between the two, and the fact that these lines marking the edges of time zones are terminator lines as the sun goes around, or whichever way you want to think of it, the Earth spinning while the sun sits. The Earth spins on a given day, does a complete spin, and that, from our perspective, look at these little dots, this is our perspective. The sun is supposedly doing this at this angle, but our time zones are doing this angle. And the time zones are marking the edges, the sunrises and sunset lines are marking the edges of the terminator line of the sun. There's no way around it. Let's see, question in the chat. Are you saying that due to the supposed 23 angle of the tilt, then the time zone cannot have the same? Right, what I'm saying is it can have the same, a terminator line is a terminator line, no matter where you put, if this is a flashlight, the terminator line will be a line across the center of the ball, whichever way from the light. So if the light is right up here, terminator line is going to follow this, is going to be this, the light will go this far, but as the ball curves away, you have shadow, okay? So you can rotate this red line anywhere, any way you want, it will follow the light, okay? So maybe let me stop sharing that and see if I can find my browser window. See if I can find, let's see, Google Images and flashlight on ball. Let me share that so you can see what I'm looking for here. Okay. I don't know if we have any animations, but let me see if I can find something. There's a little bit of one here. Let me see if I can find a bigger one. Instead of just flat, let's just have light shining on ball. All right. Let's look at this one for example. Let me blow that up. There we go. See the light? See the hot spot? The hot spot is nearest the light. If you drew a line from that light, you're going to see that this line, this is how it goes around. That's exactly what we saw in that drawing with the time zones. They curve around the surface, but if you're looking straight at the ball, if you were looking from over here, you would see a straight line going from top to bottom. If you move this light around, this shadow is going to follow. If you go at this angle, the shadow is going to follow it, and that's how time zones work. It would be nice if I could find a GIF or an animation of that. At the risk of crashing, let me find my channel. And let's see. I think that's going to be home videos. Sorry about that. Moon experiment. And I have the sound off, but you can see me moving a light around. Let me see if I can skip through here a bit. See that terminator line on the right here? There's my flashlight. There's a ball. See the line? This is daytime, this is nighttime, this is a terminator line, and that follows where the light is, okay? You see what happens to the light, to the shadow? Now the light is more toward me. The terminator line is going this way, still following from the top of the bottom of the ball. It's this this, if you take the center of this, it's parallel to the arc of the light, to the path of the light, I should say. Okay, that's what makes time zones. And if it goes away, the time zones over that would be like morning. The sun is in the east, and it's dark on this half of the ball. Time as the sun rises, the line's moving this way. It follows the light. That's why we have time zones. That edge is the mark between one time zone and another. That's also the terminator line. Okay? That's what I was trying to show. I don't know if I have anything else here I can really, because I was showing a lot of different things about how light was working on these spheres. There's a little chewed up dog toy ball Earth, but here again I'm holding the light along the equator. That's the only time those lines, the terminator lines, are going to match. Okay? And you'll have a hot spot that faces the light and the terminator line behind, which is because the ball is falling away from the path of the light. That's why you have shadow. And if you move the light around like this along the equator, you're going to get time zones, terminator lines. But in the real model, the standard model, which is not real, if I put this up here, the terminator line would be at this angle. See what I'm saying? And it would go around, the lines would go around at that angle. So I'm going to stop sharing that for now, and I'm trying to explain why we have time zones and why the angle of the line of a particular longitude follows the sun. It has to. Okay. The tilt only has different length days because that's how they're explaining seasons. But I'm talking about a rotation on one day. You understand, Charlie? A rotation on one day. I'm not talking about the seasons here. This is why I picked June solstice. Let me go back to sharing my drawing again. This is, let me zoom back in. One day, June solstice, June 21st or something like that, okay? I didn't say the terminator line determines time of day. I'm talking, you're mixing things up, Charlie. Time of day is where the sun is in your time zone, okay? The path of the sun through one day. Time zones are within an hour, okay, but the terminator line is still changing. Even within one day, the terminator line is moving. You're just in such a small thing inside that zone of light that you don't see the terminator line until sunrise or sunset. I didn't say the time of sunrise and sunset was important. I said the line, the angle of sunrise and sunset as it relates to time zones. Because if we put the sun at the equator, you will get time zones as we know them. And the reason you get these lines running parallel north to south is because the sun's at the equator, and that's where the terminator line is going. I showed you in that video that this line, this arc, if the light's over here, on the other side of the Earth, you're going to see sunrise following this line. If you're anywhere on this longitude, it will be daylight beginning at the same time. Okay? Everybody north, everybody south is in the same time zone. Therefore, they're seeing sunrise at the same time all along this edge of the ball. And this moves. This edge is going to keep moving because that's the terminator line between light and dark. Here's the light of the sun coming around at the equator. This is the, if you were to draw a terminator line in the Earth at every hour, okay, every hour throughout a day, you would get lines like this. But it only works at the equinox. At other times of the year, sun is going to be throwing a shadow at an angle like that, up to that angle, 23.5 degrees. This one, day is on this side or day is on that side, whichever end of the earth is getting most of the sunlight, but the angle is going to be the same. It's going to keep varying between straight up and down and 23.5 degrees. You never see the time zones vary. For example, everybody along this line gets daytime, say it's 8 a.m. or 6 a.m., okay? That would work on the equinox. Would not work when the line is going this way. That would mean people here are getting daylight the same time as people up here. That's the problem. Yes, it is, Charlie. I don't know how I can explain this anymore. The terminator line is the edge of a time zone. Do you understand? No, I'm not inviting anybody in. I'm got to focus, and I know your reputation there, Brenda. Sorry. And it's not about fear, or I wouldn't be doing these videos. If you want to comment, you can comment after the video is over, or here in the chat. The science is undeniable here. We observe sun path, and we observe time zones that a person here at this edge is seeing sunrise at the same time as a person down here in Central America, okay? Because that's the terminator line of the sun as it's coming around. This only works at the equinox. When the sun is at any angle, the terminator line will follow it, as I showed in that video, and the time zones should be angled as well, and they're not. So, yeah, you can kick him, her out. Brenda has a man voice. It's from, I've heard Brenda on chats before on Hangouts, and Brenda has a guy voice. So I'm not interested in that sort of thing going on here. So anyway, do you understand, Charlie, that the line between time zones, that line, that's what I'm talking about. That's what these lines are, the lines between time zones. What is this line between time zones? That is sunrise. Okay? Sunrise. These are sunrise lines. Does that help, Charlie? Sunrise lines. Sunrise. Okay? Because the sun's moving this way. Each of these lines represents sunrise for the people in that area, that time zone. That's a sunrise, sunrise, sunrise. Okay? If the sun's up here going at this angle across, which it is, most of the time, or this angle, one of the, see this is a nice handy angle here. That's sunrise line has to follow it because it's a terminator line. Why don't you, here's a thing for you to try at home, Charlie. Get a rubber ball, mark, get a flashlight like I did in my moon experiment video, and hold the lights, parallel to the ball, and just so you barely see a crescent, okay? And then take a marker and mark the edge of that crescent. And then move the light a little bit towards you, still keeping it parallel to the center of that ball. Mark the next crescent. I guarantee you, by the time you're done, you're going to have lines like this. Now, do the same experiment. Move the light up here and go across the earth like that. Go across the ball like that with your light. I can guarantee you that you're going to have a bunch of lines like this going across. They won't match. I can guarantee you that. And you'll still say, those aren't time zones. But I'm sorry, if you ask any physicist, astronomer, anybody who understands lights on a sphere, they will tell you that time zones as they are marking the edge, the terminator lines of the sun as it goes around the earth. That's how they work. No, no, no. The lines between time zones, sunrise, that line, not the whole zone. And even if you want to make that high noon, okay, all these represent is when light reaches. If I'm in the Eastern time zone and they tell me sunrise is at 6 a.m., you're telling me it's at noon. That's what you're telling me, Charlie. When you say the time zones are marked by solar noon, I can tell you, you can look at timeanddate.com. Solar noon in my time zone right now in the east here is at 1:40 p.m. Okay? Is that when sunrise was? That's solar noon, not sunrise. This line represents sunrise. The line between zones represents sunrise because right now it's dark because the light's over here. It's in darkness. So this line between time zones represents where a person on this side of the line is seeing the sun. This one isn't seeing it yet. So as soon as this line crosses that person, they see sunrise. Charlie, do you understand that solar noon is when the sun is high, and that when you have a terminator line, that's when the light is barely visible? Sunrise. Sunrise. Do you understand that the reason we have two time zones here is not because just now it's solar noon, We're talking about this line between them, which is sunrise, 6 a.m., 6 p.m. at the equinox. Okay, say we're at the equinox right now. Make it easy. Right here along this whole line is going to be 6 a.m., not noon. This line, okay, it's a terminator line. I can't explain it any better than that. Political reasons. Okay, they can't change where the light is. Nobody can change where the light is. They can decide whether it's 8 a.m. or 4 p.m. They can call it whatever hour they want. That's what is done politically. These are not political lines. These are light lines, terminator lines. And what if you want to call this sunrise 4 o'clock in the afternoon, you can call it that. I don't care. That's political. It's like daylight savings time. The sun really rises. Solar noon right now is at 1:40 p.m., like I said. 1:40 p.m. makes no sense with solar noon. Solar noon, all you're doing with political is changing what hour you call it. You can't change when you actually see the sunrise. The sunrise, this line, the terminator line between the zones, is when you see the first light. And that's how they mark these lines. That's how they mark them. Now, if you want to tell me that when the sun is up here, that you can see the sun, say the tip of Florida here, and all the way up here in, say, Washington, not DC, but Washington State, that's what you're telling me is possible. That you could see the sun all the way from Florida to Washington State when the sun is at the June solstice. That's what you're telling me would be true, regardless of political drawing lines. So yeah, I agree, Ryan, that these problems would be really tough to discuss or even discover without instant communication. Because right now I could call somebody in Australia, although I'd wake them up. I think it's like 2 in the morning there or something, some night owl, and they would tell me it's night. They would tell me they see a particular star. And there's a little bit of over, like I think 4 in the afternoon or so here is like 6 a.m. in certain parts of Australia. I would be seeing the sun going towards setting. They would be seeing it rising. And if you follow the terminator line, that's the reason. It's the terminator line. The sun is going one way on the other side of the, it's going from the east, it's low in the east for me, or low in the east for them, and low in the west for me. But we're both seeing a little bit of light at the same time because wherever they are in Australia is just enough on the other side of the ball in the ball model that the terminator line is just about right on it. Okay. So if we have this terminator line, like right now it's daytime, like if this is sunrise, you're going to be seeing sunset on the other side of the earth. That's just how it works. That's observation. So yeah, that's what I'm saying about terminator lines. time zones are based on the fact that they'll tell you, because clock doesn't match sun. That's why we have things like sidereal time that's different from, because the Earth doesn't make a full rotation according to the sun. We set clocks for convenience, okay? The clocks will mark a rotation of the Earth, but the rotation of the Earth doesn't necessarily match the sun. That's why we have different day lengths. But what I'm saying about terminator lines is they are telling you, if you have somebody way up here in Canada that's got sunrise the same time as somebody down here in South or Central America, there's a line between those, which is the terminator line, because that's sunrise for all the people along that line, regardless of what time they call it. And you can follow that line all around the Earth. And the fact is that during the solstices, you're going to have an angle like this that would make the terminator line sunrise happen the same time in Florida as the same time as it happens up here in Canada on the West Coast. And it doesn't happen. It never happens. Never happens. You can't have those kinds of problems with the sun being anywhere but straight onto the Earth. It just doesn't work. Anyway, I can't explain it any better than that. I'm not talking about the center of a time zone. I'm talking about the edges, Charlie. Do you understand what an edge is? Between time zones, that signifies sunrise. Okay? Sun's coming this way. Each of these lines is sunrise. Sunrise. Okay? What I'm saying is, one more time, is that if the sun's up here where they're telling us, you know, the Earth is tilted toward the sun at the June solstice, the terminator line would go like this. This is more of an extreme angle, but say it's going like this. Oh, look, I got sunrise in Alaska the same time as Florida. If the sun, you know, the Earth is tilted toward the sun, spinning around at this axis, the terminator line is going to face the sun. It's going to be like this, so we should have sunrise in Alaska the same time we have in Florida. Never happens. Therefore, the standard model, this motion, is wrong. The only thing that can explain the motions we actually see is the sun is straight on to the equator, and there's some sort of lensing between us and the sun that makes it appear to have these angles that bend toward the center. That's the only thing I can think of. You go talk to him, Charlie. I'm not making these definitions. This is the physics of light. Terminator lines are sunrises. There's no disputing that. A terminator line is a sunrise. Forget time zones right now. These are terminator lines, okay? Forget time zones. That's confusing you. Terminator lines, as you move the flashlight around the ball, I can guarantee you would get lines like that. And then after you draw those lines, move the flashlight up at an angle and go along this, you know, or just, you know, keep the flashlight there, turn the ball, rotate it 23.5 degrees, do the same experiment, draw the lines, they will cross over these lines. And you will get essentially sunrise in Florida the same time as Alaska. It'll happen. Do the experiment, Charlie. Take a ball. One more time, I'll explain it. Take a ball, take a line over here, flashlight, and put it around behind the ball so that you just have a sliver of light. Mark that arc on the ball. Mark it with a marker. Move the light a little bit towards you, keeping it parallel with this line. You'll get an arc like this. Do it again. You'll get an arc like this. And pretty soon you'll have a stripy ball like that. Forget time zones. I'm talking about terminator lines now. And lo and behold, if you paint the United States on there, you line it up with true north, just like it's, you know, says here, and this is a standard time zone model, you would see lines very similar going straight up and down from the true North Pole to the true South Pole. The United States lined up like this, okay? You're going to see that. Now, mark your lines again, only this time rotate the ball this way, 23.5 degrees. Keep your light here. move it around the equator, mark your lines. I can guarantee you're going to have lines like this. I'll have to do that experiment for you sometime just to show you what I'm talking about, because you don't understand. Terminator lines follow the light. That's what markings between time zones are, political or not. Like here you can see, here's a political line. Okay? But Terminator lines don't lie. You will never see sunrise in Florida the same time you see it in Alaska. You will never see that. Observation. Okay? I'm going to have to do that experiment sometime just to put this to bed, because no amount of explaining is telling you why it is that you will never see the sun's Terminator line falling on the Earth. You will never see it go like that. I'm going to have to get a big ball, paint the US on it, line it up to its poles, and show you how I draw the lines. I'll draw the lines, and then I'll just show you how the Terminator line matches the curves, and then I will rotate that ball and do it again. Okay, I'll have to do that sometime, because no amount of explaining seems to be working. I've tried everything. This is my third video, and all I can tell you is that these are observations as to the sun's path on one day, this June solstice. This is the sun's actual observed path. It starts up north of east. Solar noon, it is south of my location. Okay, south of my latitude by, this should be 90 degrees at solar noon. It's not. It's more like 70. And then it goes back northwest. Opposite problem here. We're still north. It's still north, but when you're on this side of the ball, north means you're leaning toward the center, toward north, and it rises northeast, sets northwest, only it has solar noon north of your latitude instead of south. That's what I'm illustrating here. And at the equator, even within the tropics, we're going to have a line that's parallel to the equator. That's the sun's path. It's always 90 degrees overhead. That's what I'm showing here. But this is what we should be seeing, and we're not. The only line on the June solstice that matches this path, observed path, is in the south. Okay? These don't match at the June solstice. The sun is supposed to be doing this. All of them should be pointing toward the sun, the Terminator line. They don't. The only way to explain what we do see with those lines pinching at the top toward the center is this kind of a lensing effect. That's all I've been trying to say. I will have to do that experiment. I do want to get off of this and show one more thing. Midnight sun, by the way, Charlie, happens only at the poles, and only when that pole is pointing toward the sun, in which case you won't get any Terminator lines at all. If you take the flashlight and point it up here and spin the ball, you won't get a change in Terminator line. That should be pretty self-evident, but I've had enough of trying to explain that. Now let me show a different window here, just to make one little point. Anyway, okay, so you're in. Thanks for coming. So what we got here is the four corners of the Earth. Getting back to the biblical model just for a second. Four corners. What did the word corner mean in Greek or Hebrew? Both the Greek and Hebrew words, I looked them up, they mean an angle. They mean, it's where we get, in Greek, the word pteros, P-T-E-R-O-S, which we get, you hear the word pterodactyl. It means wings, extremities, flaps, anything that would curve over something else or cross over, and that's all related to a convergence point, an angle. That's the ancient understanding, okay, of what an angle was. And so if you wanted to mark a quadrant on a circle, you would put this plus line on it, and you would get four angles, four corners, but they're internal. Okay? What I'm saying is, to the Christians, is that four corners of the Earth doesn't have to be on the outside. It can be the center, can be the four corners of the Earth. But what they mean by extension is the 4 quadrants. Now, you won't get the word quadrant directly from the ancient understanding, but you will get the fact that there's an internal angle of something, an internal angle, as opposed to an external angle. External angle would be a box around this or even a box inside this. But an internal angle is just taking the center and marking 90 degrees on it. So you can have 4 corners of the earth, literal meaning of corners, per the ancients, and still understand that they're talking about the 4 quadrants. Okay? I understand that a corner is not a quadrant by definition, but when they say the 4 corners of any kind of circle, and the Bible also calls the earth a circle, the only way you can reconcile corners, 4 corners of the earth, and the circle of the earth, people have tried to put either a square around the earth or a square inside. But even if you put the square inside, you would have to go like north, south, east, west would make sense. In other words, you would have this angle of the box going from here to here. I should have drawn that, but I didn't think of it soon enough. Anyway, that would also give you the 4 corners. But then it makes you wonder, you know, it really amounts to the same thing. If you put a square from here to here to here to here, you're still going to get a square inside a circle. And the Bible says that people are drawn from the 4 corners of the earth. So you could say they're drawn from the north, south, east, and west extremities, but it doesn't make sense when the context is indicating God is drawing people from everywhere, and then he says the 4 corners. Even if he's talking about these 4 points, he's talking about the fact that these are the extremities, and that's a very true meaning to the original word, either in Greek or Hebrew, of that is translated corners. They are extremities. Even in Daniel 9, in that prophecy thing that I've gone over, it says about the abomination of desolation happening on a wing or extremity of the temple. Same word. So when you take them all into consideration in their context, you're talking about extremities or corners, okay? Either one. And if God is talking about drawing people from the 4 corners of the earth, he's talking about the 4 extremities. Why 4? Because you can take an internal 4 corners of a circle. That's the only way I think is the best way to, not necessarily the only way, but the best way to reconcile the 4 corners of the earth with extremities as the meaning of the original word, and corners all along with that, and it's referring it to the 4 quadrants. That's how I would tie those together. So I'm going to stop sharing that and see what else might be going on in chat. Oh, we're being called idiots by an idiot, so let's just get rid of that idiot. And now we'll have a hit piece on me saying I called somebody an idiot. But and of course, there are people who record the chats and everything, and so they can, use it to do hit pieces. And those people have no life. They can put that in their hit piece too. Anybody who spends their time trolling other channels just to look for something they can do a hit piece with has got issues, to say the least. So anyway, these interpretations of the Bible are what was at that time. Okay, I'm going back to the original ancient understandings. You can look it up. These are the meanings you will look in any decent lexicon of either Greek or Hebrew. You will find that the word in Greek and the word in Hebrew both have the same semantic range in this case, and they mean corners or extremities or things that are the edges of things that are flapped over to cover something else. That's where, like I said, where you get the word pterodactyl. It has wings. It's something that flies. So the pteros part, P-T-E-R-O-S, is the extremities, the wings. And when you have internal extremities, you're talking about an internal cross point. And so when the Bible talks about 4 corners, talking about this cross point here, and these are the 4 corners of the earth. Even if you put the corners of a square inside the circle, you'll still get the same idea. So I'm not the one who's inventing interpretations. Everyone had those interpretations at this time in history. Any other interpretation is an invented one. So there you go. You can look it up on any scholarly site to do with ancient Near East languages. Look at the Hebrew of BC up to, AD. Look at the Hebrew. The Old Testament, of course, the last book was written, I think, several hundred years, I think up to 400 years, depending on the estimate, before the New Testament was begun. And the Hebrew meant the same thing as the Greek word teros in the first century. It meant corners, extremities. You can look it up in any lexicon. So if you're going to keep telling me that I'm making up things when you're the ones making it up, you can just leave, find something else to do. This won't be of interest to you because you clearly have not studied ancient languages or the Bible, and that's what I'm talking about right now. So have fun someplace else, band people. You get what you deserve. And as far as the astronomers that Charlie may be working with, and maybe he is, I don't know, but they need to explain terminator lines to him. But like I said, I'm going to have to do an actual physical experiment and draw the stupid lines on a ball, move the light around, and then angle the ball and do the experiment again and draw the lines. You will see crossed lines. And then I'll try to draw a rough outline of the U.S. on the ball in line with the north-south, true north pole, as it's shown on any ball map, and show how impossible it is to work, because at the June solstice, the line would make sunrise happen at both ends, both the east and west coast of the U.S. at the same time. Can't happen. But I'll have to do that because my drawings aren't working, even though I try really hard to make good drawings. So anyway, yeah, this is a big deal. And in the future, after I do the real ball experiment with a marker, I'll have to do this on various flat Earth maps because I think they will have similar problems. You have to have lensing of some sort if you have one sun, and I can't even make myself go to the trouble of debunking the multiple sun model. There are people who believe that, and I'm just not even going to take my time for that because time is limited. At any rate, I don't think most ball earthers understand the problem. That's the reason I did this, is because these lines that go north to south pole all the way around the ball are terminator line markings. And we mark them every 15 degrees because that's how long it takes the sun to move 1 hour, so to speak, if we measure 24 hours. And on a clock face, that would be, each number on a clock is 30 degrees. Because if you divide a 360-degree circle by 12, you get 30 degrees per number. So if you look at the sky as a clock face, and you want to know how the sun moves in the space of 1 hour, you would mark it, the numbers on the hour numbers on a clock face would be 2 hours. So that's why, and you can verify this, if you make a sundial that you're going to angle the whole dial up at your latitude, you will mark from 6 a.m. to 6 p.m., mark each hour 15 degrees apart. That's why they work. Those are terminator lines. You can prove it by the fact of a sundial. The sundial, a horizontal one, is more complicated. If you do a sundial that the whole dial is angled up at your latitude, okay, and facing away from the sun's path, and you mark the bottom half of that, if you have a circle, and you can buy these online to download and print and fold it in a certain way at your latitude, and you put a stick through the center. You will have a half circle at the bottom with each hour marked, and I can guarantee you if you measure those hour lines with a protractor, you will see that they are exactly 15 degrees apart. So anyway, it's just a matter of understanding how light moves on a sphere and why we mark 15 degrees apart, and why the standard model of the angle of the Earth's tilt toward the sun doesn't match with the lines of time zones forget time zones, sunrise arcs. We'll call them that. Sunrise arcs won't match any model. And as I said, midnight sun is at poles. It's a completely different animal at the poles. It'd be like shining a light at a ball where you're holding the light in front of you and holding the ball in front of you, and you spin the ball, nothing's going to change. Terminator line will stay where it is. It will stay small. I mean, no matter which angle you put it, the terminator line will be, depending, the size of the circle of light will vary depending on how far you are from the sun, but from the light, the ball from the light. But the terminator line will not vary. If you just spin that ball on its axis and the axis is pointing at the light, you will have no change in terminator line. So anyway, now Charlie claims that longitude lines are based on the positions of the stars. Like I said, if you're in a time zone and somebody else is in the next time zone west of you, it's dark there. If it was strictly based on the stars, it wouldn't have anything to do with sunlight. And yet it does. What's the point if saying sunrise is at 6 a.m. right now in my time zone, say, for example, it isn't, but say it's 6 a.m. in my time zone, an hour away from me to the west, sun hasn't risen yet. It's a different time zone. They don't mark those according to the stars. They mark them. If you look at the time zone ball again, let me show that one more time. Let me go get that. Because it's really hard, I guess, to visualize. You see those lines, time zone lines from any time zone site? They go true North Pole, which is pointing at Polaris, because that's the axis of the Earth's spin. Axis of the Earth's spin. And look at this, at the equinox, it's gone straight up and down, 90 degrees. 90 degrees. And if you were to mark, solar noon, so I can guarantee you sometime during the day, solar noon at this point and the equinox, you're going to have it right 90 degrees right in the middle at any rate. Yes, as I've explained, north points toward Polaris. But that's not why these lines point there. They point there because that's the Earth's axis of spin. That's the axis of spin. That's why they mark terminator lines here, or time zone lines. They all converge at the true North Pole and the true South Pole. They converge there because that's the axis of Earth's spin. That's why. It has nothing to do with the stars. It has, the only way you can extrapolate that is by saying that, well, the axis of the Earth's spin points toward Polaris. Yes, it does. I said that at the very start of this video. It points toward Polaris. But that's not why these lines are there. They point there because that's the axis of the Earth's spin. Charlie, I've had enough of you. Go do the experiments. Maybe sometime I will still do the ball thing. And I will prove this to you. The reason those time zone lines converge there is because that's the axis of the Earth's spin. But the problem is, this also happens to be the lines between them are sunrise lines. That's what I'm calling, not time zones. I'm calling the edges sunrise lines. You misunderstood me, and I'm tired of it because you're wasting my time now. I will do the rubber ball flashlight line marking experiment. I need to set up things so that the ball turns consistently. That's the hard part, because trying to put a stick through, what I'm going to have to do is buy a globe that's already at the angle and already has a pole through the middle of it, so to speak. So I don't have to balance it. So nobody can say that I did something wrong. I have to go buy a plastic globe and do this. Is this a Charlie Sock account? Being banned doesn't mean he can't listen. That's ridiculous. All right, I'll block you too. I already don't have any viewers. What are you talking about? I'm not worried about viewers. I'm not here to be popular. I'm here to be accurate. I'm here to make a point about the standard ball model not working. That's all I'm making the point about. I'm saying that these terminator lines don't add up when you're at a solstice. They don't work. You should have sunrise in Florida and Alaska at about the same time or thereabouts. If the June solstice, the Earth is pointing toward the sun. That's the way the terminator lines should go, and they don't. That's the way the sunrise lines go, and they don't. I'll ban you all if I have to, but you will behave in my chat. Okay? Insulting the channel owner is not going to get you kept here. I don't care about viewers. And all banning does, it does not stop you from viewing. You're still here viewing, aren't you? All banning does means you can't annoy me with stupid comments or insulting comments, and you can't ruin my chat and ruin the people who want to actually talk about what I'm talking about intelligently. You won't get in their way anymore. So yeah, a time zone line between time zones is a sunrise line. That's what it is, a sunrise line. Okay, a sunrise line is a terminator line. And these lines also happen to roughly match the edges of time zones, because we can see right here, I'm pointing at the wrong thing, sorry. We can see right here that it's daytime, like this is, you know, the daytime on the eastern part of the United States, Eastern time zone, and it's still dark. When it's light here, you know, this is, say, sunset line, where it's going to be. It's dark over here because the sun hasn't turned that far. The Earth hasn't turned that, rotated that far in the standard model. And that's why it's dark, because that's a terminator line right there. This is the whole time zone. This is sunrise for these people, sunset for these people. I don't know how else to explain it, but I will have to draw those lines, because apparently drawings don't work. I don't know why. I've tried everything to illustrate it. I don't know what else to try. Oh, let's ban the spammer. I'm glad they can't post links. Hey, Mark. See, this is what trolls do. They get their sock accounts and start pelting you with garbage, just to ruin the chat, just to rankle the channel owner, just to be trolls, and then they'll go whine and make hit pieces about being trolls. You don't believe terminator lines is straight? Well, on a ball they wouldn't be. I mean, from a tiny person here. If you look at the horizon at sunset, say, for example, if you're looking this way, well, here I am pointing at the wrong thing again. If you're here and you're looking this way, you're looking at the sunset, okay? From your tiny perspective, you're going to actually, the Earth looks flat and circular from your perspective. So you're going to see, every way you turn, you're going to see the same line and a circle around you. That's the dark line. So what I mean by straight is going this way on a ball, because what I'm doing right now is just looking at the ball model, okay? Just looking at the ball model. And I will show, if you look right now before I do the actual next video on actual rubber ball with lines marked on it, I have a video called Moon Experiment in my home videos playlist. And you will see a hotspot. That was a big issue in that video, was the hotspot and the fact that we don't really see one on a full moon. But that's not what I'm talking about. The terminator line is where the light has fallen away around a ball to the point where the ball is turning away from the light and you can't see it anymore. That's why it's in the dark. That's what a terminator line is. But if you are on a flat disk, it's simply where the light just doesn't throw that far. Like if you shine a flashlight, you've seen the model of a flashlight circulating, pointing down, straight down, perpendicular to a flat disk and going around in circles above it. The light will only reach so far. And that light will also be curved around you. It will curve around you. So what I mean by these straight lines, straight is simply meaning that it follows between one pole and the other at like a wedge around a circle. So if you go back up to this line is straight because it's going straight to the center. But if you draw a sunset line or terminator line, which is the edge of a time zone, you draw a straight line and the outside of this ball is going to be curved because the ball is curved. Like if I draw a straight line from north to south, if I draw it looking at this edge of the ball, it's going to be straight. And as I showed on my, it'll be curving away from me, but I can't see that, so it looks straight to me. And that's what I showed on my moon experiment video. Whereas you would get, like with the phases of the moon, if the light's coming from over here, you're going to see an arc like that. So what I mean by a straight line is if you're looking at going back here to the time zone map, if you're looking straight here, this is a straight line, okay? It's curving away from you, but that's what I mean by a straight line. And the terminator line will follow that arc. And when it gets halfway, when the light is exactly over here, then you will see a straight edge. It's curving away from you, but it's straight vertically. Not straight horizontally, but straight vertically. And then as the light continues to move, it will bend that way. So I recommend looking at my moon experiment video for that. And yes, you will see hot spots. All right, well, stupid spammers. And hit peace in 3, 2, 1, so to speak. I mean, it's not the first time, won't be the last. Take a number, get in line if you want to do a hit piece on me. You wouldn't do them on your own people or yourselves who make terrible accusations against other people all the time. They're like, let me just say something briefly about bullying, because this has happened to an unnamed popular Flat Earth channel recently. They had this following and they gained their notoriety, gained their following suddenly, and started out bashing Christians, okay? Bashing Christians, dividing the Flat Earth community, bash, against the Bible, against Christianity, hate and division. And then they did all these good things for the Flat Earth community. Everybody forgot about it because they apparently have the memory of a goldfish. Everybody forgot about the hostility, hate, and division this person did at first. And then later, this person's activities and attitudes toward others came back on him. His channel, he had to take a bunch of stuff down, and people said, oh, that poor guy, the haters won. Never mind what he did to other people. When it came back on him, he whined and cried, and now he's got even more sympathy from people with short memories or blind spots who don't care what he's done to others, only what others have done to him. That's bullying. That's what bullies say, bully on a playground. They will provoke other kids. They will punch other kids, hurt them. And then when the other kids have finally had enough and they snap and they punch back, the bully makes sure this teacher sees it and goes crying to the teacher, oh, look, that bad kid over there hit me and picked on me and stuff. That's what bullies do. See it all the time. That's what these trolls do. They needle you. They try to post, get you to go visit porn sites or whatever it is. And then when you ban them, they cry to mommy. They go run to the teacher. They make hit pieces. Oh, what a bad person I am. So bad Christian. There you go. I've already beat you to it. So anyway, I've covered the topic I wanted to cover. I need a drink. I need a rest. So I'm going to stop sharing that screen. And I guess the next thing, instead of working on what the problems are with Sun Movement on standard Flat Earth models, I'm going to have to get a cheap globe somewhere and start marking marker lines all over it and show people why time zones are the way they are. And let's ban another sock before we shut down. And I'll see you guys with another ball and flashlight experiment to illustrate things I can't do by drawings and I'm guessing that even that won't work. What can you do? Nobody can say I haven't tried, that's all. So thanks for anybody who came, and Here again, yes, the point today was to see what's wrong with the standard cosmology, not to offer a solution necessarily, other than the lens, the double concave lens, that would do it. So thanks, guys, for coming, and you all have a good day, too.